Have you ever wondered what makes a nuclear bomb so incredibly powerful? It's not just a bigger version of a regular bomb like dynamite or TNT. Those bombs get their energy from a chemical reaction, which is kinda like rearranging the furniture in a room. A nuclear bomb, however, completely changes the room itself. It gets its energy from a nuclear reaction, which happens deep inside the very core of atoms, the tiny building blocks that make up everything. This process unlocks an amount of energy that is millions of times greater than any chemical reaction could ever produce. The science behind it is both fascinating and, frankly, a little scary. Imagine you have a single molecule of TNT. When it explodes, it releases a certain amount of energy. Now imagine a single nucleus of an element like uranium. When that tiny nucleus is split, it releases about 20 million times more energy than that one TNT molecule. That is a mind-boggling difference. This is why nuclear weapons can cause destruction on a scale that is difficult to even comprehend. They don't just create a big explosion, they unleash the fundamental forces that hold matter together, creating conditions hotter than the core of the sun right here on our planet. It is this fundamental difference in the energy source that sets nuclear weapons apart from everything that came before them. The energy from a nuclear reaction is released in several forms. A large portion of it becomes kinetic energy, which is the energy of motion. This is what pushes everything outwards in the explosion. Another part becomes intense heat and light, which we call thermal radiation. Then there is gamma radiation and other invisible particles that can be very harmful to living things. All of this happens in a fraction of a second, creating a chain of events that is devastatingly effective. Understanding this release of energy is the first step to understanding the true nature of a nuclear explosion and its far-reaching consequences for our world. So when we talk about nuclear weapons, we are talking about a technology that taps into the very fabric of the universe. It's not about burning something or causing a rapid chemical change. It is about altering the nucleus of an atom to release a colossal amount of stored energy. This is why a device that can fit inside a missile can have the power to destroy an entire city. This incredible power, derived from the smallest particles we know, has shaped global politics, warfare, and our very perception of what it means to be safe in the modern world. Science has unlocked this power, and it's important for all of us to understand it. There are two main types of nuclear weapons, and they work in opposite ways. The first type is the atom bomb, or what scientists call a fission bomb. The word fission simply means to split apart. These bombs use heavy elements like uranium-235 or plutonium. The idea is to take the large, unstable nucleus of one of these atoms and split it into two smaller pieces. When this split happens, it releases a tremendous amount of energy, along with a few extra neutrons. These neutrons then fly out and strike other nearby uranium or plutonium nuclei, causing them to split as well. This creates a chain reaction. This chain reaction happens incredibly fast, with each split causing more splits, and those splits causing even more. It's like a line of dominoes, but instead of just one domino knocking over the next, one domino knocks over three, and each of those three knocks over three more. In less than a millionth of a second, trillions upon trillions of atoms are split, releasing a massive burst of energy. This is the technology that was used in the bombs dropped on Hiroshima and Nagasaki in 1945. Fission bombs are powerful, with yields that can be equivalent to hundreds of thousands of tons of TNT. But they are actually the simpler type of nuclear weapon. The second type of nuclear weapon is the hydrogen bomb, also known as a thermonuclear bomb. Instead of splitting atoms apart, these bombs force them together. This process is called fusion, and it's the same process that powers our sun and all the other stars in the universe. A fusion bomb uses light elements, typically special types of hydrogen, called deuterium and tritium. Under conditions of extreme heat and pressure, the nuclei of these hydrogen atoms are slammed together so hard that they fuse to form a heavier element, like helium. This fusion process releases even more energy than fission. To get the extreme temperatures and pressures needed to start a fusion reaction, we're talking about millions of degrees Celsius. A hydrogen bomb actually uses a small fission bomb as a trigger. Think of it as using a match to light a giant bonfire. The fission bomb explodes first, creating a blast of X-rays and intense heat that is contained within the bomb's casing for a moment. This energy is directed to compress and heat the hydrogen fuel, kicking off the much larger fusion reaction. This two-stage design allows for bombs with almost unlimited power, far exceeding what is possible with fission alone. Let's imagine a 1 megaton nuclear bomb, equivalent to 1 million tons of TNT, detonating above a large city. What happens in the very first fraction of a second? The moment the chain reaction begins, whether from fission or fusion, the core of the bomb reaches a temperature of around 100 million degrees Celsius. This is many times hotter than the center of the sun. At this temperature, everything inside the bomb, the metal casing, the nuclear fuel, the electronics, is instantly vaporized into a superheated plasma. This tiny expanding ball of plasma emits an incredibly intense flash of light, primarily in the form of X-rays. This initial burst of energy is so powerful that it heats the surrounding air to millions of degrees, creating a rapidly expanding sphere of incandescent gas. This is the fireball. For a 1 megaton bomb, this fireball grows with astonishing speed. Within just 1 second, it can expand to be more than a mile wide. Everything inside this zone, buildings, roads, trees, people, is not just burned or melted, it is vaporized. The matter that once made up the heart of a city is turned into a glowing radioactive gas. The pressure inside this fireball is immense, many times greater than the atmospheric pressure around it. The surface of this fireball glows with incredible brightness, briefly outshining the sun. Its surface temperature is about 5,000 to 8,000 degrees Celsius, which is similar to the surface of the sun itself. For about 10 seconds, this man-made star hangs in the sky, radiating a terrifying amount of heat and light in all directions. Anyone who looks directly at it, even from many miles away, can suffer permanent blindness. The sheer intensity of the light is enough to create nuclear shadows, permanent silhouettes left on walls or pavement where a person or object blocked the flash, bleaching the surface around them. As the fireball expands, it also begins to rise, like a giant hot air balloon. It pulls up dust, debris, and vaporized material from the ground below, creating the iconic mushroom cloud. This cloud is a swirling, turbulent column of superheated gas, smoke, and radioactive particles. It will continue to rise high into the atmosphere, sometimes reaching heights of over 10 miles. The creation of this fireball marks the first devastating stage of a nuclear explosion, a stage that erases a part of the Earth's surface in the blink of an eye, and sets the stage for the destruction that is to follow. While the fireball is forming, it unleashes its next wave of destruction: thermal radiation. This is essentially a massive pulse of intense heat and light that travels outward from the explosion at the speed of light. It arrives long before the sound or the blast wave. This is not like the gentle warmth of the sun. It is a searing, instantaneous wave of energy that sets fire to everything flammable in its path. For our 1 megaton explosion, the effects of this thermal pulse are felt over a vast area, far beyond the zone where the fireball vaporized everything. It is a silent but incredibly destructive force. Within a radius of about 7 miles, this wave of heat is so intense that it will cause spontaneous ignition. Paper, wood, fabrics, and dry vegetation will burst into flames without ever being touched by the fireball itself. The paint on cars and buildings will bubble and burn away in an instant. This leads to the creation of thousands of individual fires across the city, which can quickly grow and merge into larger blazes. In some conditions, these fires can combine to form a massive firestorm, a gigantic inferno that creates its own wind system, sucking in oxygen and burning with such intensity that even underground shelters can become ovens. The effect on people is horrific. Anyone exposed to the thermal flash within a radius of 8 to 9 miles would suffer third-degree burns on their exposed skin. Third-degree burns are the most severe type, destroying all layers of the skin and the tissue beneath. They are often not painful at first because the nerve endings are destroyed. Closer to the blast, the burns would be so severe that they would be instantly fatal. Even at distances of up to 11 miles, people could still receive second-degree burns, which are intensely painful and cause severe blistering. Clothing can offer some protection, but dark-colored clothing can absorb the heat and ignite, burning the person wearing it. This wave of thermal radiation is what makes nuclear weapons fire weapons on an unimaginable scale. High-speed camera footage from old nuclear tests clearly shows this effect. In one famous video, you can see the paint on a school bus instantly ignite and burn off, moments before the shockwave arrives to tear the bus apart. The thermal pulse lasts for several seconds, but the most intense part is over in a flash. It is a silent, light-speed attack that sets the stage for the physical destruction that is about to come. ensuring that even what is not knocked down by the blast may be consumed by fire. After the flash of light and heat, the next stage of the explosion arrives, the shockwave. This is a wall of compressed air moving outward from the fireball at supersonic speeds. As the fireball rapidly expands, it pushes the surrounding air away with incredible force, creating a sudden and extreme change in air pressure. This overpressure is what we call the blast wave, and it carries the majority of the bomb's destructive physical energy. It is like a hurricane-force wind, but it's accompanied by a crushing pressure that can flatten even the strongest buildings, as if they were made of cardboard. It's a pure, brutal force. For our 1 megaton airburst, the effects of the shockwave are catastrophic. Within a radius of about 3 miles or 5 kilometers, the overpressure is so high that virtually all buildings, including steel-reinforced concrete structures, are completely destroyed. They don't just collapse, they're shattered and swept away. This area is known as the zone of total destruction. Nothing is left standing. The wind speeds in this area can exceed 500 miles per hour, which is actually faster than the most powerful tornado ever recorded. Any person in this zone would be killed by the pressure wave or the collapsing buildings. As the shockwave travels further out, its power decreases, but it remains incredibly destructive. Between 3 and 5 miles, that's 5 to 8 kilometers, from the explosion, most residential homes and wooden buildings would be completely leveled. Even heavily built concrete buildings would suffer severe damage, with their frames twisted and walls blown out. From 5 to 7 miles, or 8 to 12 kilometers, residential buildings would suffer extensive damage, making them uninhabitable. Windows would be shattered at distances of 20 miles or more, sending razor-sharp shards of glass flying at high speeds, which can cause terrible injuries to anyone nearby. A strange and final blow comes after the main blast wave passes. The explosion creates a massive, low-pressure area where the fireball used to be. Air from the surrounding high-pressure zone then rushes back in to fill this vacuum. This creates a powerful reverse wind, sometimes called the negative pressure phase. This secondary blast, while not as strong as the initial shockwave, can be powerful enough to topple structures that were already weakened and damaged by the first wave. It's a final, violent gust that completes the destruction, pulling wreckage back toward the center of the explosion. In the minutes and hours after the fireball, thermal pulse and shockwave have passed, the true horror of a nuclear attack unfolds. The city is gone. In its place is a smoldering, radioactive ruin. At the center, a crater of fused glass and earth marks ground zero. For miles around, the landscape is a flat plain of rubble, shrouded in dust and smoke. The thousands of fires started by the thermal radiation are now merging into larger conflagrations. If a firestorm develops, it will rage for hours, consuming everything that can burn and raising temperatures on the ground to unbearable levels. The human cost is beyond imagination. Those who were in the zone of total destruction are gone. Those who survived the initial blast and heat in the surrounding areas are likely to have horrific injuries, severe burns, broken bones, and internal damage from the pressure wave. Medical facilities, if any are still standing, would be completely overwhelmed. There would be no electricity, no clean water, and no way to call for help. The first responders, firefighters, police, and paramedics, who would normally rush to a disaster scene, would themselves be among the victims. The survivors are left to fend for themselves in a toxic and chaotic environment. Then comes the invisible killer radioactive fallout. The mushroom cloud, which has now risen high into the atmosphere, is filled with radioactive particles. These particles are a mix of unfissioned nuclear fuel, byproducts of the explosion, and dirt and debris that were sucked up from the ground. As the cloud is carried by the wind, these particles begin to fall back to Earth, blanketing a huge area downwind from the explosion. This fallout emits dangerous radiation that can penetrate the body, damage cells, and cause a deadly illness known as acute radiation sickness. The effects of fallout can last for days, weeks, or even years. The most intense fallout occurs in the first 48 hours. Anyone who is exposed to high levels of it will suffer from nausea, vomiting, and internal bleeding, and will likely die a painful death within a few weeks. Even lower levels of exposure can cause long-term health problems, including an increased risk of cancer and genetic damage that can be passed down to future generations. The land itself becomes contaminated, making it unsafe to live on or grow food for many years. A nuclear explosion doesn't just destroy a city, it poisons the very earth it stands on. To understand the power we're talking about, it helps to look at real-world examples. The first atomic bomb used in warfare, codenamed Little Boy, was dropped on Hiroshima, Japan, in 1945. It was a fission bomb with a yield of about 15 kilotons, meaning it had the explosive power of 15,000 tons of TNT. While this is considered a very small nuclear weapon by today's standards, it was powerful enough to destroy a city and kill an estimated 140,000 people by the end of the year. The devastation it caused introduced the world to the terrifying reality of the nuclear age. Just 9 years later, in 1954, the United States tested a far more powerful device at Bikini Atoll in the Pacific Ocean. This was the Castle Bravo test, the first test of a dry-fuel thermonuclear bomb or hydrogen bomb. Scientists had predicted a yield of about 5 megatons, 5 million tons of TNT. However, they made a miscalculation and the bomb actually exploded with a force of 15 megatons, 3 times more powerful than expected and 1,000 times more powerful than the Hiroshima bomb. The fireball was nearly 4.5 miles wide, and its mushroom cloud reached 25 miles into the sky. The unexpected size of the blast caused widespread radioactive contamination, affecting nearby islands and a Japanese fishing boat, the Daigo Fukuryu Maru. But even Castle Bravo was not the most powerful nuclear bomb ever detonated. That title belongs to the Tsar Bomba, or King of Bombs, tested by the Soviet Union in 1961. This was a hydrogen bomb designed to be the ultimate show of force. Its original design had a potential yield of 100 megatons, but for the test, it was scaled down to 50 megatons to reduce the amount of radioactive fallout. Even at half strength, it was a monster. The fireball was over 6 miles in diameter, and the flash of light was visible from more than 600 miles away. The shockwave was so powerful that it circled the Earth 3 times. The Tsar Bomba's explosion was more powerful than all the explosives used in World War II combined, including the 2 atomic bombs. The plane that dropped it was over 70 miles away when it detonated, but it was still hit by the shockwave and dropped a kilometer in altitude before the pilot could regain control. The bomb's mushroom cloud soared to a height of 40 miles, well into the upper atmosphere. These historical tests, from the city-destroying power of Little Boy to the planet-altering force of the Tsar Bomba, serve as a stark reminder of the incredible destructive potential that humanity has created. After the world witnessed the power of nuclear weapons, a new and dangerous chapter in human history began. The United States and the Soviet Union entered into a Cold War, an intense rivalry that stopped short of direct fighting. Instead, they competed by building up massive stockpiles of nuclear weapons in an arms race. At the peak of the Cold War, the two superpowers had a combined total of over 60,000 nuclear warheads. This was enough to destroy every major city on Earth, many times over. The question became, why have so many weapons if using even a few would be a global catastrophe? The answer lies in a strategy called deterrence. The idea is that the best way to prevent a nuclear attack is to have so many weapons of your own that you can guarantee a devastating counterattack. If another country launches nuclear missiles at you, you will still have enough weapons left to launch a massive strike back at them. This concept became known as mutually assured destruction, or MAD. The logic is chilling. The only thing preventing a nuclear war is the certainty that nobody could win one. Both sides would be completely annihilated, so neither side would be foolish enough to start one. This strategy of MAD led to the creation of what is known as the nuclear triad. This means having nuclear weapons available to launch from 3 different platforms, from land-based silos, containing intercontinental ballistic missiles, or ICBMs, from submarines hidden deep in the ocean, and from long-range bomber aircraft. The purpose of the triad is to ensure survivability. If an enemy launched a surprise attack and destroyed all of your land-based missiles, you could still retaliate with your submarines and bombers. This made a successful first strike almost impossible and, in theory, made the world safer by making nuclear war unwinnable. Today, even though the Cold War is over, this logic of deterrence still dominates the thinking of nuclear-armed nations. There are currently 9 countries that are known or believed to possess nuclear weapons. While the total number of warheads has decreased significantly since the Cold War peak, the United States and Russia still each possess around 6,000 warheads. These arsenals are maintained not with the intention of fighting a war, but with the goal of preventing one. the world remains on a hair trigger where the peace is kept by the threat of unimaginable violence. The logic of mutually assured destruction led to some truly terrifying technological developments. Perhaps the most famous and frightening of these was a Soviet system known as Perimeter, or, as it was nicknamed in the West, the Dead Hand. This was a fail-safe, automated system designed to guarantee a retaliatory strike even if the entire Soviet leadership was wiped out in a surprise attack. The system was designed to be activated during a crisis. If it was turned on, it would constantly monitor a network of sensors for signs of a nuclear explosion on Soviet soil, seismic vibrations, light flashes, and radiation. If the sensors detected a nuclear attack, the system would then try to communicate with the military high command. If it could not establish a connection after a certain amount of time, the system would assume the leadership was gone. At that point, the dead hand would take control. It would automatically authorize the launch of special command rockets that would fly across the Soviet Union, broadcasting launch orders directly to the country's remaining nuclear missiles in their silos and on their submarines. In essence, it was a doomsday machine, designed to ensure that even a dead country could fire back. The existence of a system like Dead Hand shows how extreme the logic of deterrence became. The goal was to make retaliation so certain, so automatic, that no enemy would ever risk a first strike. While Russia has never officially confirmed the current status of the perimeter system, many experts believe a modernized version of it still exists today. This highlights the ongoing risks of automated warfare and the possibility of a catastrophic accident or malfunction. It is a stark reminder that these weapon systems are designed to work even when humans are no longer in control. As we look to the future, the challenge of nuclear weapons remains. Today, the world's largest nuclear arsenals are smaller but more technologically advanced. Missiles are more accurate, and warheads are sophisticated. While the threat of a massive, all-out war between superpowers has faded, the risk of a smaller-scale nuclear conflict or a terrorist group acquiring a weapon has grown. Understanding the science behind these weapons, the fireball, the blast wave, the fallout, is not just an academic exercise. It is essential for understanding the world we live in and the immense responsibility we have to ensure that these weapons are never used again. The power of the atom is awesome, and it demands our respect and our vigilance.